Okay. Just a quick announcement. We have a physical chemistry seminar this week. If you're free on Friday and you're not in the seminar class, if you are in the seminar class, you're coming anyway. I've invited Brett McGuire from MIT. He's a new professor at MIT. He's not much older than me. He's probably about the same age as I am. He'll be speaking to us out at Kaplan, actually just right here, next hall room over, 11 o'clock on Friday. Brett is a very well-known and young career kind of successful scientist, but he's an astronomer. He's an astrochemist in particular. His background is in molecular spectroscopy. He's a physical chemistry major. He got his PhD in physical chemistry. But he spent his postdoc and his postgraduate life surfing couches throughout America being an astronomer. So his specialty is using spectroscopy to identify chemistry and new molecules in space. So his specialty that he's going to talk to us about is this idea of looking at carbon, formation of carbon-containing molecules in space. The reason why this is very interesting is that the origin of all chemistry is this, right? All complex organic molecules that we know and love and consume on a regular basis all get created in the interstellar medium around young stars, right? So the idea is finding carbon that's cold at the early stages of star formation. This is where complex chemistry actually begins. Many of the places where chemistry happens in space tend to be hot, right? And stars and things like that. They're so hot that neutral atoms barely exist. And so these cold regions that are dense in ice and dust, they're really good regions to make molecules. And that's where molecules get made. Methanol, ethanol, the simplest molecules you can think of, acetone, right? These are all made during the early stages of star formation. And so Brett's specialty is using spectroscopy combined with radio astronomy to look at these star-forming regions and look for molecular signatures for molecules and then use that information to build chemical models for how these things form. Brett's a great speaker, very charismatic. So if you're interested in this topic at all, I highly recommend coming. Brett is in some ways the expert in the field that isn't over the age of 40. He is. There's a good reason why he's at MIT. He's a very talented scientist, so I'm very happy to have him here. The reason why I got him here is he's a buddy of mine, of course, so there's always a connection. But he's a great speaker, and I highly recommend coming if you're interested in that. That's about all the announcement I have for that. We have a number of other astrochemists coming in a couple of weeks, and I'll announce them as we go through. We have a theorist coming, a friend of mine, Chris Schingeldecker. He's a computational guy who studies chemical models for interstellar chemistry. And then we'll have a talk from Ilsa Cook, who's also a new professor at British Columbia in Vancouver. She's a laboratory scientist. So she's a laboratory chemist who tries to model interstellar conditions in the lab and understand chemistry from a laboratory perspective. So we have an observational guy, we have a theorist, and we have an experimentalist coming in this month. So I'm really excited about this series. Okay, that's all I have to say about this. We're moving topics today. In fact, this will be a new module. We've now more or less completed our traversal through thermodynamics, and now it's time to use it on something. And what we're going to use it on today is one of my favorite topics, probably the most fundamental outside of chemical reactivity, if you will. We haven't quite gotten to reactivity yet, but talk about physical transformations of molecules and chemicals. It's the idea of phases. And what I want to do today is I'm not going to sit here and talk about gases and liquids and solids and what are the differences. We can talk about that. I really want to talk about the concept of phase transitions. In particular, the idea of converting from one phase to another. So we're more concerned with the act of phase transitions, or a phase transition. There's a phase transitions instead of the physical form of matter, instead of the physical structure of different phases. The interesting thing about phase transitions is there are many different kinds of phase transitions. Well, as we'll learn, there's basically two. There's more than one type of phase transition, I should say. And it's not entirely clear what's the difference between the two. For instance, we can think of, let's just stop for a second, and let's think about the different kinds of phases that we have. How about someone yell out a phase that they know of? What's a phase of matter? Yeah, gas, of course. This is an interesting. This might seem really trivial, but you bear with me. What are some others? Liquids. What's another one? Solids. What's another one? What'd you say? Plasma. Someone want to define what a plasma is?
Superheating gas.
Yeah, it's not only that. It's a highly ionized fluid of charged particles. All right, you have particles. You have so many charges inside a plasma that the electromagnetic effect, the attraction and repulsions between positive and negative charges become so strong that they're the primary binding force in the liquid, and so the dynamics of a plasma are built around electrostatics. Any others? Any others? I guarantee you there's another phase of matter in this room that is literally sitting in this room that isn't any of these. Does anyone have any guesses? What's that?
I'm trying to mention dark matter.
Yeah, well, okay, so that's true. And I don't know how to define dark matter. That's an interesting topic. There's it's a question of whether dark matter forms this particular phase or not. It depends on how you look at it. But something more common than dark matter. There's another phase of matter that's in this room right now besides these five. Any guesses? This one might throw you for a loop. Glass. Glass is a unique stable as a phase of matter. In fact, what it's called is a metastable phase of matter. And what that means is it's out of equilibrium, if you will. It's not an equilibrium phase of matter. You to form glasses, you pull a fluid way out of its phase diagram very quickly, and it gets trapped into this glass phase, which is somewhat like a solid. But solids and glasses have very different properties. And in fact, the transition, as we'll learn, the phase transition from a molten liquid, think about glass, right? Like normal glass, silicate glass, or borosilicate glass. The phase transition from a molten liquid to glass is not the same kind of phase transition as a liquid to solid. It's a different kind altogether. So glasses have unique phase properties and also have unique transitions compared to the other common forms of liquid. Maybe we'll talk a little bit about glasses, but what we're going to, any others? There are more. Does anyone else know other ones?
There's the one like Einstein, like Bose.
Yeah, Bose-Einstein condensate. Where are you going to guess?
Whatever it is, the cornstarch water makes.
Oh, a non-Newtonian liquid? Yeah, I think that still counts as a liquid, but that's interesting. There are Newtonian and non-Newtonian liquids. That has to do with their mechanics. That's an interesting point. That's more of a dynamical effect than it is a phase effect, but yeah, there are different types of liquids for sure. Bose-Einstein condensate. This is what's called a quantum phase of matter. We won't talk about these so much, but certain types of atoms and particles, if you cool them enough, imagine a solid, right? Think about the atomic structure of a solid. Or a crystal, right? You have atoms in particular positions. They're all separate from each other, right? But they're all kind of fixed and rigid. And a Bose-Einstein condensate, the position of every atom in that condensate is in the exact same position. They all have the same positional state. So if you have a Bose-Einstein condensate of 100 atoms, there's a probability distribution will they'll be, but they're all on top of each other. Right? And that requires these particles to be what are called bosons. We're not there yet. We'll talk about that next semester. But specific types of particles, for instance, rubidium atoms or some sorts of potassium isotopes, or called bosons. Nitrogen-14 is another good example of a boson. They actually have the ability. You have the ability. There's nothing stopping you from stacking an arbitrary number of bosons in the same position. Every atom can exist in the same region simultaneously. And so gases, if you cool them, certain types of gases, if you cool them low enough, will condense into this new quantum form of matter at very low temperatures. We're talking microkelvin to nanokelvin, very cold, where all the atoms are in one region by themselves, stacked on top of each other. In fact, you can't pull each atom out. What you can only measure is the number of atoms inside of this region. But they're all on top of each other, spatially localized at the same place, right? Which is very strange. So there's a lot of really cool physics with that. There's a couple other ones. Does anyone else have any other guesses before I put another one down? There's another one we'll talk about briefly called superfluids. This is also a quantum state of matter, but it works. This is a exotic liquid at low temperatures. That has no viscosity. It's a completely unviscous liquid. I'll show you a video of it. A really great example of superfluids is helium-4. There's a superfluid transition around 3 Kelvin. I forget where it is, but if you cool liquid helium low enough, it goes through another phase transition to a new liquid form where it becomes a superfluid, and it becomes non-viscous. So for instance, I'll show you a video of it. It's actually really cool. If you have a bath of liquid helium, and inside of that bath, you have another container, okay? And so inside of this outer region, you have some liquid helium. So here's our helium, right? And the inner container is empty. And then as you cool, and so it works like a normal fluid when it's at liquid temperatures. And then when you cool it to superfluid, what you find is that the liquid runs up the container and fills the interior as if it had no drag. And so superfluids can go through porous membranes, materials that liquid helium can't because it has no viscosity. And the physics of that are really bizarre and really crazy. It would take a whole semester to really talk about them. But it has very fluid-like appearance. It looks like a fluid, but somehow it magically moves in ways that no other fluid can. Okay. Basically, it magically appears on the other side of this empty container. It can travel over. It can circumvent gravity and come through. Right. Very very amazing white liquid. There are other more exotic phases of matter. A really interesting phase transition, I wouldn't really call this a phase of matter, but it is a magnetization of solids. It goes through, so for instance, iron. If you take a piece of iron and cool it low enough, so if you have iron just sitting out by itself, it's not near a magnetic field, it's just kind of sitting on its own in a vacuum. Iron at normal room temperature is not magnetic. You can magnetize it by introducing it to a magnet, but iron by itself at room temperature is not magnetic. But if you cool it down to a certain low enough temperature called the Curie temperature, named after Marie Curie, iron suddenly becomes magnetic, all right, and it undergoes a phase transition. And the physics of that phase transition from non-magnetic to magnetic is precisely the same phase transition that we see in glass and in superfluid transitions, right? Even though these seem to be very different dynamics, the phase transitions are very similar in terms of their physics, as we'll see. So magnetization is an interesting phase transition. Of course, there are other types of phase transitions into the superconductors, for instance. The idea of going from a normal conductor to a superconductor is a phase transition that has to do with this Curie temperature as well. There are other types of phases as well. But these are kind of the big ones. So I kind of want to characterize today, what I want to characterize are common phases, but I also want to characterize what is a phase transition, right? What do phase transitions look like, and how are they different amongst the different types of phases that we transition through? So I want to start simple today, and then I'll show you some exotic stuff by the end of the class, and we'll talk more about it. I don't have an eraser. Oh, it's over here. Yeah, dark matter is an interesting one. There are arguments that the reason why the universe exists and there are massive particles in the universe is considered to be a phase transition. That sometime very early after the Big Bang, the universe undergoes a phase transition from a system that is a giant primordial soup of energy into something that's where the particles that we know and love get masses and are distinguished from each other, right? There was a point in the early universe where the difference between a proton, a neutron, and an electron were they were the exact same particle, right? There's a symmetry between them. There's nothing different between a proton, neutron, and electron until you get to low enough temperatures and energy, and they suddenly become different particles. So the universe also underwent a phase transition at some point. And that's the reason why particles, for instance, have mass, and we have different kinds of particles, which is the start of chemistry, of course. Okay, so again, we know from the van der Waals approximation that gases and solids, or gases and liquids, coexist. Right? We saw. Right, this was a big part of your homework. Homework 2 was that if you plot molar volume versus pressure, that at high temperature you have a gas, right, greater than the critical temperature. You have a gas-like compression diagram. And then once you get to a reasonable enough temperature, you have a curvature change like this. This is at T equals Tc. And then as you begin to cool more, there's a region where the pressure and volume are flat. Right? And we interpreted this flat region, here, where volume is not really dependent on pressure, or vice versa, as the gas-liquid coexistence region. The idea is that as you continue to compress the gas in this region, you're not compressing the gas, you're just condensing it. So this is further compression leads to condensation. Okay, so just by the fact that we introduce a size to our particles and an attraction to our particles, we magically predict that liquids exist, right? That there's some phase that the gas converts into that causes this flattening of the compressibility curve, or the isotherm. It's T less than Tc. Now, what may be interesting when we look at this graph, we might even notice that you've gone from two complete different behaviors. Right? In some ways, this curve right here looks like nRT over V. Right? Looks like a gas, but over here you don't have that same functional form at all. Right? You get this flat. It looks like a cubic function. Right? You have something that looks completely different. Right? And so that must mean that something drastic occurs at the critical point, right? You've gone from one type of physics, which has coexistence and liquid and all that junk, right? This cubic form, and you've gone to a place where the curve goes to 1 over V, to gas form, and it happens right at the critical temperature, right? So if T is greater than Tc, you have the gas-like curve, and less than Tc, you have a liquid-like curve, right? And so the transition in a gas from T less than Tc to T greater than Tc is also a phase transition. Something is going on with our gas, right? There's a certain temperature in which the gas never becomes a liquid, never, no matter what, never, there's no liquid ever. And then suddenly, once you get to that temperature and lower, liquid begins to form, right? So in some ways, this fluid that we're describing here undergoes a transition from gas, so something that can generate liquid, to not generating liquid. And it turns out that's a phase transition too. The critical transit, the T, we'll call it the TC transition, is what's called the supercritical transition, or the critical transition. Or it's a transition from gas to supercritical fluid, right? We don't really have a term for it other than supercritical fluid. The idea is that at T equals Tc, the difference between a liquid and a gas ceases to exist. Right? You can compress the bejesus out of this gas at really high temperature, and it's still going to have similar compression to a gas, but you might be at pressures where it should be a liquid. And in fact, it'll have properties that are like a liquid. Right? And so this idea that once you're above the critical point, the supercritical fluid, is somewhat the difference between a gas and a liquid just ceases to exist. They're one and the same, effectively, right? So a supercritical fluid, there's no gas or liquid. It's just a supercritical fluid. Some parts of it look like a gas, some parts look like a liquid. And below the critical temperature, you have a distinct separation of the gas and the liquid phases. This in and of itself is a phase transition, right? So supercritical fluids are in of itself a phase that is distinct, uniquely distinct from gases and liquids, right? But as we'll see, the physics, the energy, the thermodynamics of this phase transition is very different than the gas-liquid transition. And I want to talk about that briefly. Usually I introduce phase diagrams here, but let's not get there. I want to talk a little bit about the different types of phase transitions, because I think that's really where the interesting stuff is. Yeah. Here's another way to look at this phase transition, this supercritical phase transition. I think this is a really nice way to look at it. You can plot as a function the temperature of a fluid in Kelvin versus the density. Right? You can do this for any liquid you want. I'm going to use two colors here. All right, and what we can do is we can take, let's say we're in a coexistence region, right? So we start at lower temperature than Tc, so we have a liquid and a gas phase simultaneously. So we have two different components with different densities. Of course, liquid is more dense, so we'll write the liquid at the top. Right? What you find is that as a function of temperature, the density of a liquid decreases, right? No surprise. And if you look at a gas as you approach T equals Tc, now let's stop for a second. Let's just think physically. For an ideal gas, do you think that the density of an ideal gas will increase or decrease as you increase the temperature? Yeah, it should increase. Actually, it should decrease, right? That gas wants to push away from itself. It has more thermal energy and wants to pull away. Right, so the idea is that as T increases, this needs to be satisfied, so N over V, which is density, decreases, so they're equal and opposite. But in fact, as you get towards the critical point, so let's let T equals Tc here, what you find is that the gas no longer decreases, but increases towards there. So what happens is that as you approach the critical temperature, the liquid density intercepts the gas density, right? And when you have two components that have the same density, then they're one phase, right? This is just one phase. So you have one phase. Actually, let me write it differently. The idea is that within this region, you have two phases for these temperature regions. And then beyond it, you have one phase. So you've gone from a system that has two phases, the liquid and gas, to one that has one phase. Obviously, there's a phase transition going on there. Right? And this is what I was trying to get at. Right? The critical point is where you have a phase transition from a system that has a coexistence between liquid and gas to one that has no coexistence anymore. In fact, it's just one fluid. There's no difference between liquid and solid and gas. Interestingly, we can go measure the heat release from this, right? Maybe we're interested in the thermodynamics, right? We're going to heat this liquid up, this fluid up, the gas liquid fluid, to the critical temperature and then go over the critical temperature, right? So let's go from, for instance, CO2, gas liquid, and we want to go to CO2, all right, we'll call this supercritical, right? This is supercritical outside. So I'll call that SCR, I guess, supercritical. SCF, supercritical fluid, to SCF, right? So we have a phase transition. And I want to ask the question, what's delta H for this transition? So I go into the lab. Actually, before we do that, let's also look at this. Let's look at something equivalent. Let's take CO2 solid and go to CO2 liquid, and also ask the question, what's delta H? All right, so let's first do the easy one, solid to liquid. Right? In order for a solid to convert the liquid, you need to absorb heat, right? Because you're going from an ordered phase to a disordered phase. You need to pump kinetic energy into the system to break the solid apart, right? So a solid to liquid transition is endothermic, right? Delta H is less than 0, right? And what about delta S for this reaction? Does S go up or down?
S always goes up.
Right, S always goes up. Well, unless you're going the other way, then it goes down, but for the system. But yeah, but this, if you go the opposite way, entropy decreases for this system, but entropy increases on the outside because you release heat to the outside. So entropy of the environment increases. Right? So now what about this transition? Well, we go and measure it. We measure it 0. No heat's released. It's as if nothing happens energetically. Right? This should tell you something. These are very different processes. Right? You can take out any chemical out of the stockroom and do this process for it. Solid to liquid, liquid to gas. It doesn't matter, right? We can do the same thing for CO2 liquid to CO2 gas. And you find that delta H is less than 0 and delta S is greater than 0. But for the supercritical fluid transition, there is no heat of evolution. There's a very distinct change in physics here. And it turns out that this was not lost on physicists and chemists for a long time. And so when you look at the theory of phase transitions, you realize there are two particular classes of phase transitions. We call these the Ehrenfest classification, after Paul Ehrenfest, a famous 20th century physicist. Ehrenfest classification. And Ehrenfest says that there's two primary classes of phase transitions. There's what's called a first order phase transition. And a first order phase transition is a phase transition that releases heat, latent heat, or transfers latent heat, right? Enthalpy changes. Right? Delta H is less than 0, delta H is greater than 0. There's another way to interpret it, which is that first derivatives of Gibbs free energy experience a discontinuity at the phase transition temperature. Now, what does that mean? It means if you take Gibbs with respect to volume, Gibbs with respect to temperature, pressure, and you track that as a function of temperature as you go across a phase transition or whatever variable you're using, you'll notice that it radically changes. Let me show you an example of that. Let's, for instance, consider, if I can find my notes for it. Here. And I wrote a bunch of stuff down for it. Oh, they're over here. Yeah, very good. So for instance, let's think about, let me write over here. Let's consider some derivatives of Gibbs free energy. Here's a really easy one. Take the derivative of Gibbs with respect to temperature at constant pressure. Just do a little bit of math, but it ends up being negative entropy. Okay. Right? And so what that means is that on a first order phase transition, entropy change has a discontinuity. What this looks like is, for instance, let's for instance consider I don't know, H2O solid to H2O liquid, right? The fusion, or the opposite of fusion of water. And we plot as a function of temperature the entropy. So I'll put a line, we know where the temperature for this is. It's at 273, 15 Kelvin. And what you find is, so lower than this, it's a solid, and above temperature, it's a liquid. What you find is really low in entropy for the solid. And then when you go across that barrier, the entropy jumps to the liquid value. Right? It's not continuous. Right? So entropy, right? There's a jump. Right? Entropy, just as a reminder, right up there, entropy is the derivative of Gibbs with respect to temperature. Another example would be volume. For instance, the derivative of Gibbs with respect to volume at constant temperature, pressure is the molar volume. We plot T versus V. The molar volume of the solid is quite low, quite high, moles per liter. No, liters per mole. Liters per mole, yeah. So quite small. And it doesn't change that much, right? A solid is a function of temperature. Its volume doesn't change that much. It's not very compressible, so it's flat. Here's our phase transition temperature. It's basically flat. And then it jumps up because of the liquid. And the liquid, of course, is slightly more compressible. So it increases slightly. And we could say this is S to L. And just to plot it on the same plot, we could do the same thing for L to G. Maybe it goes like that. And then for a gas, it jumps up a big time, and then it goes increasing, right? Gas, of course, the molar volume increases the temperature significantly, right? This is a first order phase transition. So that, right, these second derivatives, these first derivatives with respect to Gibbs are discontinuities at the phase transition, right? So, and they also release heat, right? So things like liquid to solid, liquid to gas, solid to gas, right? Sublimation, right? These are all examples of first order phase transitions, right? Excuse me. Another interesting idea is to think about the heat capacity of these as you go across the phase transition. And first order transitions have a very, very strange property with their heat capacities. So if we plot T versus CP for, let's do liquid to gas. It doesn't really matter. But going from a condensed matter to a less condensed matter. So this is T vapor, if you want. So the heat capacity of a liquid is lower than a solid. Is that right? I think that's right, yeah. What you find is that as you approach from the left for first order phase transition, so again, we're just going liquid to gas here. The phase, again, for a liquid, the heat capacity is pretty constant with temperature. Doesn't change too much. But what you notice is that as you start to approach Tvap, it diverges. Diverges to infinity. And then when you go over that phase transition, well, it just goes back to normal, and you're at the heat capacity of the gas. So something like this. And the reason why this is quite physical, because during a first order phase transition, all heat input goes into the physical work of converting one phase to another, and not into increasing the heat or entropy of the latent phase. So let's think about when you boil water on the stove, right? The water temperature heat increases until you hit the boiling point. And what happens to the temperature of the liquid at that point when it starts to boil? Does it keep increasing as you apply heat? It doesn't. It doesn't, right? Because all of that heat is, right, the only time, right, for instance, the best way to do this actually is to measure the temperature of the pot. And what you find is that the temperature of the pot increases until the phase transition occurs, and then the pot temperature stays constant, right? Because what you notice is that when you lose all the water and it's all gone to vapor, the pot temperature skyrockets because there's no water to absorb that heat. But the temperature just stays relatively constant or close to at constant pressure. That's the important thing, at constant pressure. At constant pressure with an open pot, the temperature of the water stays at 100 Celsius at boiling, as long as you have water. Because all of that energy that you're putting in through the oven, the stove, is going into the phase transition. Right? The phase transition requires an absorption of energy from the surroundings to go from liquid to gas. And every joule that you're pumping into the system from your stove goes into that process, right? So that means that the temperature of the liquid never heats, no matter how much energy you put into it. So the heat capacity skyrockets, right? Because it takes infinite energy to increase the temperature of a boiling liquid by 1 degree. And then once you get over that boiling temperature, everything goes to normal. Okay, and that's a classic characteristic of a first order phase transition. That is true for all of these. Is that when you're at the phase transition and you pump energy into it, you're never going to raise the temperature of that transitioning fluid or material because all of that energy is getting used for the phase transition to either due to the absorption of latent heat or the emission of latent heat, depending on which direction you're going. Or sorry, this is the absorption of heat and the emission of heat. Okay, so the heat capacity skyrockets in a first order phase transition. Okay, so for instance, if you ever come across a phase transition, well, now you know how to test it. You can look at the volume, you can look at the heat capacity as you go across that phase transition as a function of temperature, and if there's discontinuities, then you know it's first order. All right, and it turns out that first order phase transitions follow this behavior universally. It doesn't matter what material it is, what transition it is. The only difference between a liquid to solid transition, a liquid to gas, or a sublimation is the magnitude at which these values change. You're going to have a less significant jump in entropy if you go from liquid to gas as you would from solid to gas, right? But the behavior, the curvature of the curve, of the derivative, if you will, as a function of temperature, is precisely the same for every material. It's universal. So that leads us to, that must mean then that the supercritical transition, which evokes no heat, no delta H equals 0, must not be a first order phase transition. So there's another classification, not surprisingly, is called a second order phase transition. These are more commonly called continuous phase transitions. Of which there are many. But a second order phase transition is a phase transition that evokes or that transfers no latent heat. So delta H is equal to 0. But there's also a definition in terms of the derivatives. It's called second order because the second derivatives of Gibbs energy are discontinuous at the phase point transition. Now, what the hell is a second derivative of Gibbs? We've talked about a few, just not in this terminology. So for instance, the second derivative of Gibbs with respect to temperature at constant pressure is the heat capacity divided by temperature, for instance. And the second derivative of Gibbs with respect to pressure at constant temperature is equal to minus the molar volume times the compressibility. How compressible the system is. These have discontinuities in the second order phase transition. Compressibility factor. How compressible it is. There are many others. But these are the more relevant ones, I would say. And so what a second order transition looks like for CP make sure I have this right. I have a figure of it right here. Is that it doesn't diverge. So let's look at CP as a function of temperature for a second order transition. It doesn't diverge, but it is discontinuous. Actually, let me change this. Sorry. This actually looks more like this. Sorry. Like that. Is that right? Yeah. Actually, so the curvature is not exactly right. Let me just get it right. It's like this. It kind of increases. Oh, geez, this is a tough one to draw. It's like this. Like that. Kind of, it goes off like that for gas. There's no discontinuity. It goes to infinity and then comes back down and increases like a gas does. So for a second order phase transition, like going from a regular fluid to a supercritical fluid, CP diverges. Like that. No, sorry, no, it doesn't do that. Sorry. It's discontinuities, it doesn't diverge. I apologize. I always get these mixed up, I'm sorry. So so it goes like this, and then there's a discontinuity and it continues. Like that. All right, because there's no latent heat. Right? So any heat you put into the system doesn't go into the phase transition because the phase transition doesn't require any heat. So the heat capacity doesn't diverge. It just changes values. So for instance, if this is gas and this is supercritical, right? The heat capacity of the supercritical fluid is different than the gas, but the gas one doesn't diverge because there's no heat required to make the phase transition. Very strange behavior. There's other types of approaches. So for instance, let's look at first derivatives for second order transition. If we look at volume as a function of temperature, the volume increases and then it just keeps going, right? There's no discontinuity. Right? In a first order phase transition, you have discrete differences in the volume, a molar volume of a liquid and a solid, but in a continuous phase transition, they just move. The curvature changes. Right? That's sloped more on this side than it is on this side, but they're continuous, right? They meet in the middle. There's continuity. Same with entropy. Entropy looks precisely the same. Like precisely the same. All right, so there are two very different kinds of phase transitions. And it turns out there's lots of really beautiful results that come out of this, which I'd like to show you a little bit. This is just qualitative, right? I'm not doing any math here. I mean, okay, there's derivatives on the board. That would be a lie. But the idea is that you have things that you can measure: the volume, the entropy, the heat capacity. These are just qualitative ideas, and you kind of have a sense of what happens to them, right? But we're not doing any calculations here. This is just if you were to measure these, this is what it would look like, that you see two discrete different types of phase transitions. So I want to show you some cool stuff. I have some plots for the last 10 minutes or so of some things I want to show you about these transitions, because I won't show you a lot about first order because you see these every day, right? You see ice melt and you see water boil. I don't need to show you these things. They're not that interesting. I mean, they are, but you've seen them a million times already. Instead, I want to talk about these continuous transitions. And it's really hard to look at these things until you actually it's hard to understand them until you actually see it. So let me turn on my screen. All right, here's this. Let me change my OBS real quick. Okay. Yeah, so here's again, so enthalpy, volume. This is chemical potential. We haven't introduced that yet. Entropy and CP versus first and second, and you can see that they flip-flop depending on whether they're first derivative or second derivative. What I want to show you is a video of a supercritical phase transition. Okay, so hopefully this will work. Right, I don't know what liquid this is off the top of my head. If this even, of course, I pick a video and then it doesn't work. Maybe I have to turn editing on. It worked this morning. Enable content. This was a YouTube embed. It wants to go. Oh yeah, there we go. I don't remember what liquid this is off the top of my head. You'll have to apologize. But so before we start, we're heating this liquid up, right? So we have a coexistence of liquid and gas, right? You can see the bubbling through it. You'll see it in a minute once I replay it. And we're heating it towards the critical point for whatever liquid this is. I forget what it is. It might be sulfur hexafluoride or something, or some mixture. All right, and let's see what happens. So again, you have gas bubbles being bubbled through the liquid. Everything's kosher, exactly what you would expect. And then as you start to approach the critical point, I don't know when that happens, but it will right here. The whole thing clears up. There's no more separation between. Let me pause it for a second, and I'll resume it for Lucy, so she can see the action. Right, so we start with a two-component mixture of liquid and gas, and then once you reach that critical point, the whole thing goes cloudy. And that's at that point, right at that critical point, where the density of liquid me draw it on the board here. Let me just raise the screen real quick. Let me finish the video while I talk about it. You guys are sitting here probably like, geez, let me just finish the damn thing. And so what's happening here, if we think about temperature versus density again, we have the gas and the liquid coexisting. And what's happening is you've gone from a two-component mixture, and then simultaneously the entire fluid continuously goes into one fluid, right? That shows one phase, one layer. That's this cloudy mess. And there's a reason why it's cloudy. Because in fact, the density of this fluid is fluctuating wildly. Think about the temperature of this material. Hold on, let me display me real quick. And let me switch my presentation over. Oh, it's already set up. Okay. Think about this flask, or this test tube rather. Right? You have a fluid inside of there, and imagine you can measure the temperature at different points. Of course, there's going to be a temperature gradient because you're not heating it evenly. Right? So there might be some cool regions. Okay, bear with me. Some cool regions, or some hot regions, whatever you want to call. There might be some cool regions and some regions that aren't so cold, or more cold, and some hot regions. Right? You have a temperature gradient. Right? So if you think of this as x, as z, the z direction, the dt dz is not equal to 0. Right? There's some gradient in temperature, right, as a function of position. Right? There's some colder pockets and higher pockets. So let's think about how the density changes as a function of temperature at this point. Right? So you're near the critical point. So what does dp dt look like? d rho dt look like? If you're close to the critical point, like right here, you can see dp dt kind of has a strong slope. But as you start to get closer to the critical point, the slope gets more and more extreme to the point where you're at the critical point, the slope is infinite. Right? The tangent line relative to the critical point on this curve is straight up and down. Right? So tiny fluctuations in temperature lead to huge, I'll write this more clearly, near the critical point, tiny fluctuations in temperature lead to huge fluctuations in density, right? Right? Because the slope of that curve is basically infinite at the critical point, because dp, so if you take the limit as t goes to tc of the derivative of density with respect to temperature at t equals tc, this equals infinity, right? Positive infinity, or negative infinity, just approaches infinity, right? As you increasingly get closer and closer, it becomes more and more infinite, or closer and closer to infinity. And so small fluctuations in t lead to huge fluctuations in rho. And so what happens is that small deviations in the liquid lead to these crazy density changes where the liquid is continuously moving in and out of a liquid-like density and a gas-like density, which leads to that cloudiness. Right? That cloudiness is the fact that you have these micro fluctuations in temperature leading to huge density fluctuations. So the system is at this critical point is constantly fluctuating between one phase and two phases, one phase and two phases, one phase and two phases. And this process is called critical opalescence. Right? The material becomes, at the critical point, opalescent, which means that it's effectively opaque. Opalescence, excuse me. Close enough. The system is constantly moving between these phases, two phases, one phase, two phase, one phase. So it's very murky, very chaotic, which leads it to be extremely cloudy. And you have very, very chaotic behavior. And that's because in second order phase transitions, so for instance, let's think about freezing ice. This is an amazing thing about second order phase transitions. I love this topic so much. You'll have to forgive me.
Cypher, this board.
Yeah. What's that?
This board.
Okay. Okay. It's not on the camera, so let's think about. Let me get a blue marker. Let's think about liquid water freezing. All right, so we got some liquid water here, and you want to freeze it. So how does it typically freeze? Well, typically what happens in a freezing process is that you first form a crystalline nucleus. Right, you form a small crystal here, which then allows you to propagate the crystal elsewhere. Right? You always nucleate a crystal, and that allows the system to crystallize out in this. So in a freezing process, freezing occurs typically spatially local, and then over time freezes the whole sample. Right? When you freeze ice, it takes a little bit of time to freeze. You start to see, like when you have ice cubes, right? Your ice cube begins to freeze out, but not all of the liquid is frozen. And it takes a while for the whole thing to freeze. So for a first order phase transition, occurs in a local way. Liquid far away from the crystallization has no long-range knowledge that freezing has begun. Right? The crystal has to propagate across the liquid to freeze. Right? Okay, so when you do a phase transition and you're sitting at the phase transition temperature for a liquid freezing, that's what typically happens. Not much happens until you have a nucleus, a crystal for other crystals to grow on. The nucleation occurs, and then eventually the whole thing starts to freeze over. But it takes time. Right? And so if the crystallization starts here, the water molecules over here on the left don't have any clue what's going on. They're like, okay, well, we're just hanging out here in the liquid. Right? So first order transitions occur locally, and they just kind of propagate over, depending on the temperature and the conditions. They tend to propagate over the whole sample. Second order phase transitions are not like that. Second order phase transitions occur collectively and with infinite range. You can have a sample of CO2 liquid or CO2 gas that's 20 miles long. Okay, you have a giant chamber that you can turn on the pressure, you can pressurize it, right? You convert it to supercritical gas. It could be 20 miles long. And you start to heat over on the left side, and as that heat, okay, that's not really fair, but as you heat the whole thing up evenly towards and pressurize it as you approach the critical limit. And what happens at the critical point, the entire liquid simultaneously changes at the same time. There is no nucleation in the second order phase transition. Second order phase transitions occur with what's called infinite correlation length, which means that if it starts to condense here, the rest of the liquid everywhere else knows that it starts to condense or change. Right? It has infinite knowledge and infinite length of knowing that a phase change is occurring. and does so in a continuous fashion. The whole thing converts simultaneously. Right? That's why we saw that critical opalescence. Right? There's no nucleation going on. The whole liquid starts to equilibrate at the critical point, and the whole system converts or sits right on that edge between two phases, liquid and gas, and one phase, supercritical. Once you drive it over that supercritical limit, once you're out here in the boonies, the liquid doesn't have critical opalescence anymore. You just have a nice clear liquid, right? Because there's just one phase. There's one phase, there's no fluctuations, and this transition occurs continuously across the entire liquid. It doesn't matter how much liquid you have, it doesn't matter how big the sample is. The entire thing goes at the same time. Same with glass. I don't know if there are any glass blowers in here, but you'll know that when you convert a molten solid into glass, a molten liquid, like a silicate liquid or fluid into glass, the whole thing occurs simultaneously. There's no nucleation. The whole thing converts into glass. Might be worth looking at a video of that at some point. I want to show one more example before the end of class of these continuous phase transitions. Hopefully, why is this not showing? There it is. Of course, I want to show a video. Okay, I want to show an example. Okay, so this is a simulator of what's called an Ising model. The Ising model, it's named after a physicist named Ising, of a 2D magnetic material. Okay, imagine this to be a flat plane of iron. Okay, and each dot inside of this is an iron or some magnetic atom. And the definition of magnetism, remind you, is that, for instance, in very simple cases, you can think of an atom as being spin up. So right, it's an up arrow or spin down. We haven't talked about spin. We won't talk about it until next semester. But there's every atom has a specific property called spin, which allows it to interact with a magnetic field. And so a magnetic atom, a magnetic material, has the number of up atoms minus the number of down atoms is not equal to 0, right? So they're not randomized. So for instance, if you have a long chain, if you have a one-dimensional metal, right, a magnetic metal would look like this, where they're all matching the same side, and you have and if you interact this with a magnetic field, it would magnetize, right? So if you interact this with a magnetic field, there's a magnetic force, I guess in this direction. Net magnetic force, right? That's what a magnet is, right? A very simple form of a magnet, right? And a non-magnetic material, the number of spin up and spin down are equal and opposite, or equal. So n up minus n down is equal to 0. It would look like this. Right? And so all the ups cancel the downs, so there's no net magnetic force. Okay? That's a really, really simple way to explain a magnet, but it's fair. Right? And so the idea is we're interested in, well, is there a phase transition between these? Right? Can you take a non-magnetic material that has its spins randomized and set it and change the temperature or the properties such that it converts to magnetic? And it turns out you can. This phase transition occurs magnet to non-magnet, occurs at the so-called Curie temperature, which for most magnets is pretty low. I mean, it's like, on the order of maybe 10 to 100 Kelvin. Right? Pretty cold. It depends on the magnet. It's pretty cold. But you can do that. For iron, for instance, a piece of iron, if you cool it down low enough, it spontaneously magnetizes. It goes from non-magnetic, in the absence of a magnetic field, to magnetic spontaneously. And this is a second-order phase transition. what I'm going to show you here is a model of this. So now what we're going to do is we're going to take a 2D plane of our magnetic material. And instead of up and down, we're going to have black and white. Okay, so this is a randomized simulation of our material. You can see at this temperature, we have some pockets that are minus, some pockets that are plus. And let me turn the temperature up a little bit, actually. I'm going to turn the temperature up pretty high. Okay, so this is relative to the critical temperature, so 6 times the critical temperature. Or no, it's not. It's 3 times the critical. Critical temperature is around 2.2. So a really high temperature, and you can see everything's random, right? You can actually measure the magnetization. Let me plot that real quick. So this curve right here, as a function of time, is the net magnetization of the material. And right now it's at T equals, it's basically at 0, right? Magnetic 0, right? Because the spin up and the spin downs are equal and opposite. They're randomly fluctuating, and nothing's happening. This is what a metal looks like at high temperature. Now watch what happens as I start to decrease the temperature. So now I'm starting, so the temperature, let me restart it actually. Let it equilibrate. Right, you can see the fluctuations in magnetism. Of course, it's fluctuating, but notice that on average, it basically averages out to 0. Right, there are fluctuations, and that's due to the fact that this is an infinite. So there's going to be some fluctuation, but that's okay. But in general, it kind of looks random. But now as I start to cool it towards the transition temperature, we start to see a little structure form. But again, it's still pretty random. Right? The fluctuations are starting to increase. Right, as you start to approach the temperature, think of, instead of density, think of magnetism. The derivative of magnetism with respect to temperature is starting, the slope is starting to increase. So you're starting to see more fluctuations in magnetization. But still, on average, if you look at it and you blur your eyes, it's above 0 as much as it is below 0, so it's effectively 0. And I keep cooling it. And then what we start to see is that their structure starts to form simultaneously everywhere. Right? You're starting to see pockets, right? And based on the initial conditions, we're starting to see a net magnetization. Right? This isn't nucleation. Right? The entire system is starting to transition. I really wish I could step the temperature a little more clearly so you could see it. But as I drop the temperature, oh, awesome, I can do this. So let's set it to 3 here. Let me restart it. All right, it's relatively randomized. And now I set it to 2.5. The critical temperature is around 2.3. We're starting to see a little bit of structure form. Notice that the structure starts to form everywhere. There's no pockets of anything. Everything's starting to continuously transform. And then as I get to 2.3, you start to see the formation of more structure. And then 2.1, we should be across the critical point at this point. Now the randomness has almost completely disappeared. Right? Now you have very clear chunks of minus and very clear chunks of up and down. Right? And which leads to and then it looks like, I don't know which one's which, but one of them has more than the other, and so you have a positive. Right, there's still, as it starts to equilibrate, you still don't have a lot of magnetization, but you can see that the system is starting to arrange itself continuously and across the entire field. Right, it's not like you start here and it starts to propagate out, but the entire system, the entire material, phase transitions simultaneously. And let me cool it down to some really low temperature when we're way below it, 1.5. Right, now it's completely starting to freeze out. The fascinating thing about this is that if I were to take, it's kind of hard to show this on this simulation, but imagine I took, so this is a 256 by 256 atom simulation. Right? It's a cube of 256, it's a lattice of 256 points in each direction. If I were to take a little box right here, okay, and I were to pull it out, and then simulate that on a lattice of the same size, right? So I zoom in. Effectively, I'm just taking my microscope and taking my lattice and shrinking it down. I would see the exact same pattern that I see here. Right? The system is not only continuously transitioning from one phase to another simultaneously, but it's size exclusive. Right? It has infinite correlation length. It doesn't matter if you have a sample that is this small, a sample that is this big in lattice size, or a sample that is 10 times the size of this. You see the same patterns at the same initial conditions, right? It's size intensive. Size intensive. It's scale invariant, if you will. It doesn't matter. You see, it's almost like a fractal. Every time you zoom in, you see the same dynamics at every scale. Right? And that's what's so unique about second order transitions. I'll cool it down even more just to show you. Is that, yeah, see, it's completely frozen out at this point. Right? And I know it's hard to imagine that, but if you're near at the critical point, if I were to, this is below the critical point, but at the critical point, if I were to grab a lattice region, let me go back to that temperature one more time, 2.23, 269, reset. Right, this is very near the critical point. Right? You're starting to see this structure form. But if I were, again, as I were to take a microscope and enlarge this region right here to 252 by 256, I'd get the same picture. Okay, so a continuous phase, a second order transition it happens and has the same dynamics at every scale because of its infinite correlation length, because everything happens simultaneously. Right? So glass transitions are like this. Supercritical fluids work like this. Of course, we can't model them with these up and downs because this is something for magnetism, but the physics and the dynamics of the phase transition are precisely the same. Right? It all occurs continuously, simultaneously, with no heat release. It occurs in fluids, it occurs in magnetization, it occurs in glasses as well. So it's really unique, and you can't really get this in normal phase transitions. Okay, so that's all I have today. Starting on Wednesday, we'll come back to phases, and we'll talk a little bit more about the less exotic phases. And start talking about phase transitions a little more. Okay, have a good day, everybody.
See you Thursday.
See you Thursday.